So today, I'd like to start off by looking at that problem that we looked at near the end of class the other day, where we had the chain on the smooth surface and it slides over onto the rough surface, and we were looking for the minimum force required to pull on that chain. So I went back. I'd like you to open up, if you took notes on that question, because I got a factor that I believe was twice as big as what the solution manual has. So I have put up here on the screen the solution manual's results, and I think I just made I think there was a factor, I think we had it set up correctly if you look at your notes. I believe if you look at this expression for the velocity, I believe we had this, because I didn't have notes written down myself. Could somebody double check their notes, please? Is that velocity correct from what we had in class the last session? Mm-hmm. Okay. So then if we then set that, let the velocity, figure out what the velocity is when the entire length of chain is now over onto the rough surface, then you put in an L in here, and I think I just messed up with a factor of 2. And if you reduce that by placing L up into this equation, you can see L over L disappears, and then you end up with a radical 2 times this ratio minus this, and putting L in right here. That expression under the radical looks like this, and then if you divide both sides by 2, it eliminates the 2, and you come up with this result that the P force has to be equal to this value, which is the answer they had provided in the book. So I just missed a factor of 2, and you guys didn't catch it when I was doing it up here on the board. Also, I went back and carefully looked at the wording of the question, and it said specifically right there, we had some discussion in class about, well, what about the variable P? Because that P could vary, but it said specifically there a constant force, up I think in the first or second sentence. So you have to be real careful in the reading of these kind of questions to make sure that you get all those little pieces of the pie in there. Now there's one remaining issue I haven't yet resolved, and I want to show that to you. What we did near the end of our discussion is I said, well, let's go back and look at that acceleration expression that we originally had, which is a function of x, the amount of the chain, x being the amount of the chain that's on the rough surface. And so here's the acceleration expression, and trying to encourage you to sort of see this for its algebra structure, that this is a linear function of x. And so I ended up drawing something like this, and then I didn't get a chance to finish my discussion, but I just kind of want to leave it at that point right now, and I might come back at this again after I clarify, because I think I'm just going to let it go at that point. There's something fishy going on by plotting this and discussing, as we did in the last class session, that having this drop down to 0, this acceleration reading right when the chain just gets onto the rough surface, something fishy's going on there, and I'm not sure what it is yet. So I'll get back to you on it. And that's the way engineering frequently is. You've got things, little puzzles that come up. You might even do an experiment where you're correlating your analytical calculations with some experimental results, and you're not getting that correlation between them very well. And so then you've got to go back and see if you either did your instrumentation incorrectly or your data gathering from the experiment, or maybe made some mistakes or incorrect assumptions in your analysis. So that's the standard kind of stuff that goes on in engineering all the time. Okay. So let's see if you have any questions regarding recent work.
Pretty happy.
Okay.
The spherical stuff, we just saw them for blocks on the
Yeah, now we're starting to do particle kinetics, and we're doing it with the we were doing it with rectangular coordinate system stuff. So what I want to do is go ahead and move off of that and move on to the where we're going to use the other coordinate systems. Okay, you ready? All right. So again, we're going to stick with Newton's second law. So we're going to do equations of motion and we have the sum of vector forces equals, again, mass times acceleration. If we now look at this acceleration description, instead of looking at it in a rectangular format, if we look at it, say, in a normal tangential format, it would be, the acceleration we would write as v dot, and what direction's v dot in? Remember, this is the time rate of change of the speed. What direction's that in? Tangential to the path, plus a component in the normal direction. Remember what that one is?
V squared over the radius of curvature.
V squared over rho is the common way of expressing that. Okay? Now, while we're at it, let's go ahead and look at it if we would decide to use a polar representation for the motion. Then we have to express the acceleration in terms of an r hat component. And think about, let me just draw a little picture. Here's the particle on its path. Here's a reference point from which we can locate the object. And this is, if I use that as my defined theta, then I'm going to have an r hat vector radially from the pole, and then perpendicular to that in the direction of increasing theta is the defined theta hat direction. Okay, so now on the acceleration terms, there's a tendency for this length r to change and possibly accelerate radially. So that's what you want to keep in mind trying to remember this. And then there's also a tendency on a curved path such as I've shown here, a tendency for some acceleration to be back towards the center of curvature. And that's your clue. I call that a pseudo-normal because this is in the r hat direction, remember. R hat, and that's not necessarily that's not usually in the normal direction for generalized motion. So that's minus r what? Remember?
Theta dot squared.
Theta dot squared. So there's our r hat component of acceleration. And then we have to add to that, and this is all times the mass, remember, we have to add to that a theta-directed component of acceleration, which is in this direction then, either in the positive theta hat or negative theta hat direction. There is a pseudo-rotational one that you're familiar with that we think of r alpha, and so that's your clue to help you remember that. It's r theta double dot. And then there's the screwy one, which is the Coriolis effect, and that's additive to r dot theta dot. So we have this path-dependent coordinate system for applying Newton's second law, and then we have the polar representation here. And again, these are equal to the sum of the unbalanced forces acting on the object. So that's the concept, and we've done kinematics with this kind of stuff already, so now all we have to do is toss in the unbalanced forces. Okay? Any questions so far? Okay. Let's go ahead and work some problems then. Yes, Daniel.
And okay, say we'll imagine projectile motion with those equations, and it's because the vectors all have to add up nicely and correctly. That vector addition of an r hat and a theta hat in projectile motion would always give us a negative j hat, because that's the only direction where those accelerate. That's the only direction where
that's correct. For the acceleration, that's correct. Yep.
So we won't have any
Yep.
imaginary term like the Coriolis effect giving us a
Right. Not for projectile motion.
Of strange direction.
Not for projectile motion. Right. Okay.
Will the forces be in the same direction as the coordinate system you're using? Like,
Will the forces be in the same
we
direction
find
as the
them-
coordinate system we're using?
yeah, so like,
Well, they can be arbitrary. We can have, here's a particle.
well, I mean, will you find them in the same directions, like with respect to those axes? For instance, if you're using
Oh, yes.
the polar, will you use
Yes,
the forces?
if you have a sum of forces, like let's say I have an F1 here and an F2 here, and this one say dramatically larger, then it looks like the net resultant of these two would probably be something like that, right? So this would be the sum of those forces acting on this mass. Now, we would then describe, and we would know the object is accelerating that direction at this instant. Now, it's possible that the path is something else, right? Now, well, actually, that's not too good there. Doing that. And you know, what do you know also has to be in this direction if the sum of forces is in this direction? The vector acceleration has to be in that direction. That's why I said my little drawing of the path wasn't too good there. Because if the object has that acceleration in that, then there must be some curvature or straight line path in that direction. But if I have a curved path, then it's going to have to have some component. You know, it has to be there has to be a part of that that's towards the center of the curvature. That's why I had to draw the curvature like that. Now, back to your question, Joel, was the coordinate system you're then going to use. It may lend itself to either this or this, depending upon the motion and depending on the kind of reference that you might have. So typically, or it might be rectangular. So you kind of pick whichever coordinate system is most convenient for you to do the analysis. That seem reasonable? And sometimes you might try it one way in one of the coordinate systems, like in rectangular, and you go, oh, this is becoming untenable. And so then you stop that approach, kind of a dead end, and you maybe pick up one of these and try these. See where it takes you. Okay. So let's go ahead and look in the book and pick out prescribed problems. And these curvilinear motion equations are summarized for us on page 140, followed by several examples. And if you haven't done it, I would highly recommend that you study these examples prior to trying the homework problems. How many of you go straight to the homework? You listen to stuff in class, go straight to the homework. That's the traditional way students do it. The preferred way for the conscientious student, if you have enough time in your life, is to try to read the book ahead of time before an instructor talks about the material, right? Try to at least skim through it, get a sense of what the material's about and possible points of confusion you might have, and then listen to the presentation, then go back and study the section in detail, however much time it might take, and study the examples. Then get to the homework problems. Now, you can mix that up a little bit. You can be getting going on the homework problems and then go back to examples and study those a little bit. But there's never enough time in the classes you're taking for everything to be presented in the class. So there's a whole lot of material typically that's still in the textbook that the instructor hasn't had time to get to. So just try to give yourself enough time in your life, and I know you're all pretty busy, to spend a little more time in the book possibly. Okay. Just based on my own experience, I would suggest that. Let's look at this problem, and I'll try to zoom in a little more on that. cover up the little notes I'd drawn on there. So what we have is a rotating rod, and what we do is we rest a small mass, M, on that rod. And you want to be very careful as you move through the textbook or on exams. Notice up here, this is a horizontal axis through O. So that means the axis that's coming out of the paper down here at O, coming towards us, is on a horizontal surface. So that means this object, as this rod rotates, actually has a weight downward. Now you're going to find problems in the book and in your homework where it specifically says the motion is on a horizontal plane. The motion is on a horizontal plane. In that case, then the weight is down into your paper. So just be very careful, and notice I underlined that fact that that axis is horizontal. So the bar is rotating counterclockwise at 3 radians per second, almost half a revolution per second, pretty quick. Passing through position O, a small block is then placed on it, or when theta equals 0. The small block is placed on it when this is lying down here horizontal. As this rod now rotates upward, and the radial distance is 18 inches. The block's observed to slip when it gets to 50 inches, but it's in rotation, so it's actually got some significant motion. So when it gets up to 50 degrees, when it gets up to 50 degrees, it is observed to slip. Determine this coefficient of static friction between the block and the member. So I've drawn pretty close to a free body diagram there, and we'll put that up on the board again. So here's the weight, mg. Wait for them to kick the camera over. There we go. Here's the weight, and we're on some angle theta. So we know there is a normal force, and the angle between that normal force and mg, as shown here, is theta. Are you folks putting your normal force down here like I'm doing it? Or are you drawing it up here, pointing up?
Generally point the arrow into it.
Huh?
I generally point
You
the
putting
arrow.
it up here?
Yeah.
In physics, I think they're typically teaching you to do it up there. Is that true?
Yes.
That's kind of what I've observed. So I would encourage you to put it here. The reason in engineering I think it's better to put it here, this is just my opinion, is that this is the contact surface on which that force, that reaction force exists. And so placing that on there might be useful. Yes?
If it's a pushing force, I try to put the arrow into the object. And if it's a pulling force, I try to have the arrow go away from the object.
Okay, and that's not unreasonable. And you've seen, actually, that's the way I've done it in previous problems. You've seen where I put the force P pulling, if it's pulling, actually sitting there pulling on the object. Right?
Yeah.
Okay. Good. So we have this. Now, you make an assumption about a tendency for motion. The tendency for motion here, this thing is in rotation, and I'll put that beta or theta dot on here in a second, but it's rotating this way, and this thing's going to start to slip. Okay, so the tendency for motion we'll assume is downward. Tendency for motion is downward. Opposing that, as we've said repeatedly, is the friction force. So we're getting there on the parts. And anything else I need to put on here? Let's put the coordinate system. So I think since we have a pole here, why don't we go ahead and instead of using x, y, just go ahead and use, and we could use x, y, but let's go ahead and use the polar representation, r hat, and then make sure you place theta hat in the correct direction. Again, perpendicular to r hat, we said this repeatedly, in the direction of increasing theta, with this being our defined theta. What we're looking for is mu sub s. And what is some other information we're given?
How far it is up the
Okay,
curve.
18 inches, I believe they said. So make sure when you write that down that this distance r, make sure you convert those units into feet. There's your r distance. Okay? Feel good? Okay. And also we know that the rotation rate was given to us. This is going to be our theta dot as 3 radians per second. Constant. Constant. Now, the reason I emphasize you writing this down in your work is so that you could say then this implies, or actually what would be a better thing to say is therefore, math symbol for therefore, theta double dot is equal to 0.
From that point, can you also assume that the magnitude of the velocity isn't going to change?
Correct. So the speed, what Joel was noticing is this object has a certain speed, doesn't it? It's resting at this constant length, 1.5 feet. It's resting there even though the object's in rotation. So it is following a circular path. And so a separate little sketch might be in order. 1.5 feet. Here's the particle, and it's in circular motion. And so perpendicular here is the speed of the object. Speed of the object. And that speed happens to be r theta dot, which we could go ahead and compute if we wish to right now. 1.5 times r3, which is 4.5, and that's going to be feet per second. So we can do that. Okay.
So if velocity is not changing,
Excuse me?
acceleration has to be perpendicular. If the velocity's magnitude isn't changing,
And since the tangential acceleration you know is v dot, which would be r theta double dot, right? But we know theta double dot was 0. So we know that the tangential acceleration is 0. But it's on a curved path. So we also know
It's got a normal.
Acceleration.
there's also an acceleration this way. And notice these speed and acceleration terms I'm not drawing on the free body. I mentioned that the other day. I'm not drawing the acceleration, this normal acceleration term, or that speed term on the free body diagram. It's a separate sketch. And this is going to be, because we're in circular motion, matter of fact, we could even make a note of that. And there's some simplified governing equations that occur with circular motion. And so this normal acceleration then could be treated as r theta dot squared, or as v squared over r. Either way, you'll get the same result. So we have the, if you wish to, 4.5 squared over the 1.5. And the way I'd probably do that without my calculator is think of 4.5 over 1.5 times another 4.5. And I know this is 3, so I end up with 13 and a half. 13.5 feet per second squared is the normal acceleration. Now, notice that I use subscript n, normal acceleration here. However, I'm talking about wanting to do the problem in polar. In polar. So we're going to come back now and use the information that's here, but we're going to write our equations in polar. Okay. So why don't we go to the third board and keep in mind what we're going to do. We're going to write our sum of forces in the r hat direction, and that's going to be equal to the mass times the radial acceleration term. And then we're going to write the sum of forces in the theta hat direction, which is in our normal direction, or excuse me, our normal force direction, capital N, in that direction. And that sum of forces is going to have to equal the acceleration in the theta direction. Okay, so let's do that over here on this board. Sum of forces R is equal to mass times acceleration R. Looking at the picture, we have the friction force minus the component of weight, mg sine theta. That's it, isn't it? Okay, and that has to equal the particle mass times r double dot minus r theta dot squared. I've got it right here.
Oh, gotcha.
Yeah.
Didn't see that.
And that's it. Okay. Notice this is a scalar equation now, just in the r direction. Just in the r direction. Okay. Somebody help me out. Somebody from the silent majority. People that don't talk too much in class. Speak up. About r double dot.
0.
Zero?
It's constant.
Let's see. R is 1.5 feet, but this thing isn't moving, right? Okay, so r dot, is there any radial speed? Radial? No radial speed. And so therefore r double dot would be 0. Okay? So you want to think about these things. You just don't want to go down here and start slashing things out. You want to kind of think your way into it. Okay. So we can now knock that term out of there. And this term, r theta dot squared, is the same as that calculated normal acceleration term. And notice the negative is assigned to it, which means it's coming back towards the pole, which would be in the rotational motion normal direction, back towards the pole. So it's got that negative right there. And so the friction force then is going to have to be equal to mg sine theta minus, I move this mg sine theta to the other side, minus m times that r theta dot squared term, which we computed as 13.5 feet per second squared. Now, what were we trying to find in this problem? The coefficient of static friction. So this is a generalized force, friction force, and so at impending motion, this is where the English comes in. At impending motion, F must equal that static times the normal, static coefficient times the normal. That's when we make the substitution, at the impending motion. And that's going to be occurring. This is going to then be a critical force, isn't it? This force becomes critical to cause the break loose effect to occur. Notice that there is a static term here, a static component. Well, actually, it changes with theta, so I guess I shouldn't say it's static. Never mind. We'll just retract that remark. So then what we're going to do now is solve for this mu, and so the mu sub s is going to be equal to our mass factored out. We have g sine theta minus the 13.5, and that's got to be divided by the normal force. Now the normal force, if we come back to the other board, the normal force is going to be the sum of forces that exist in the theta hat direction. So I think we better go look at writing that equation just to make sure that the acceleration terms there appropriately disappear on us. Okay? So it's the safe bet. Rather than just saying the normal is equal to mg cosine theta, which is tempting, is just double check yourself by writing the dynamics equation. So I think so. And that should be about where we are here with this material, I believe. Yes.